Hello and welcome to Quantum Information for Engineers. My name is John Zheng. I hold degrees in both physics and engineering, and I have spent the past 30 years working as a telecommunications and software engineer. This background allows me to study quantum technology across the entire technology stack, from the bottom of the hardware stack to the top of the software stack. Physicists focus their attention on the bottom of the technology stack, where quantum waves serve as the information carriers. They have created an air of mystery and often claim that nobody understands quantum physics. If even physicists claim not to understand it, how can software engineers or even hardware engineers be expected to understand it? However, if you study quantum technology from an engineer's perspective, with a panoramic view of the entire technology stack and a zoomed-in view of the software-hardware interface, you will find it much easier to understand. The course begins by introducing the foundational ideas of classical information theory and quantum physics. Chapter 2 then provides a high-level overview of quantum technology across the technology stack. Beginning with Chapter 3, we dive into the details of how information is stored and processed in a quantum bit or qubit, and we examine its readout bottleneck, one of the most difficult yet essential subjects of this course, before moving on to Chapter 4, which covers multi-qubit quantum information theory. In the later chapters, we study several well-known quantum algorithms, including the famous Shor's algorithm. We then classify these algorithms into several design patterns, which act as conceptual bridges between real-world application problems and their concrete implementations. Some lectures in this course are narrated using my own voice, while others use a synthesized voice. One of the first questions you may ask is why quantum? Of course, we want the superior power of quantum computing, but why does quantum computing have greater power? The simple answer is that quantum computing is capable of concurrent computing. The power of concurrent computing is readily understood by computer engineers. For those who are not, an analogy is panning for gold with running water. Water and gravity act on gold and sand at the same time, and the difference in their weights separates gold from sand. We will see how concurrent computing works when we delve into quantum algorithms. The most useful quantum algorithm is Shor's algorithm, designed by Peter Shor in 1995 for fast factoring of large integers. Using this algorithm, a quantum computer could break many cryptographic systems. In particular, everyone's bitcoins would be lost. If quantum computing is so powerful, what is the catch? The catch is that we cannot observe the value changes of a quantum bit or qubit, the fundamental information-carrying device, during the computation. Doing so would disturb or distort the computation. We can only measure the qubit at the end. It is like tossing a coin. We cannot observe the landing process and can only see the result once it comes to rest on the table. Reading out the correct value of a qubit is limited by a bottleneck. Much of the difficulty in designing quantum algorithms lies in finding ways to work through this bottleneck. On the other hand, this bottleneck is a boon for encrypting communication, because only the party that knows the encryption key knows how to get through the bottleneck. In the hardware layer, the relation between hardware codes and carrier parameters is studied mainly in communication theory, for which Claude Shannon developed information theory. All communication systems use electromagnetic waves to transmit information. When we transmit a picture over a Wi-Fi or cellular network, radio waves serve as the carriers, which are a type of electromagnetic wave. However, a software engineer does not deal directly with transistor voltages or radio waves. Within the hardware layer, hardware code is mapped to carrier parameters. Converting codes from one format to another is called encoding in information theory. In communication theory, hardware codes are called symbols. Information processing or computation in a digital computer at the hardware code level consists of binary operations such as addition and multiplication. We do not need to know what happens at the carrier level, including how CPU circuitry changes the voltages of transistors and capacitors. In a quantum computer at the hardware code level, computation is a unitary matrix multiplication applied to the complex number vector of the qubits. At the carrier level, the amplitude parameters of the qubits are transformed by quantum gate circuitry. However, we will need to examine the carrier level when we study qubits and gates in chapters 3 and 4, because the output of qubits encounters what we call the qubit readout bottleneck. The ability to perform a unitary matrix multiplication using a single circuit is where the concurrent computing power of a quantum computer lies. The qubit readout bottleneck, on the other hand, makes quantum algorithms difficult to design. In the hardware layer, the relation between hardware codes and carrier parameters is studied mainly in communication theory, for which Claude Shannon developed information theory. All communication systems use electromagnetic waves to transmit information. When we transmit a picture over a Wi-Fi or cellular network, radio waves serve as the carriers, which are a type of electromagnetic wave. However, a software engineer does not deal directly with transistor voltages or radio waves. Within the hardware layer, hardware code is mapped to carrier parameters. Converting codes from one format to another is called encoding in information theory. In communication theory, hardware codes are called symbols. Information processing or computation in a digital computer at the hardware code level consists of binary operations such as addition and multiplication. We do not need to know what happens at the carrier level, including how CPU circuitry changes the voltages of transistors and capacitors. In a quantum computer at the hardware code level, computation is a unitary matrix multiplication applied to the complex number vector of the qubits. At the carrier level, the amplitude parameters of the qubits are transformed by quantum gate circuitry. However, we will need to examine the carrier level when we study qubits and gates in chapters 3 and 4, because the output of qubits encounters what we call the qubit readout bottleneck. The ability to perform a unitary matrix multiplication using a single circuit is where the concurrent computing power of a quantum computer lies. The qubit readout bottleneck, on the other hand, makes quantum algorithms difficult to design. We have just learned the first fundamental concept. Information is useful numbers. We have also learned that information is represented or carried by physical parameters. From this, we can understand that information processing, including computing, can be accomplished by changing these parameters. We now add another concept. Errors are the ultimate enemies of any information system. Some of you may have learned that one type of error is called a systematic error. Systematic errors depend on how an information carrying or information processing device is built, and they are usually correctable in most information systems. Another type is called a random error. Random errors usually come from unknown or uncontrollable sources, which are generically called noise. We hear buzzing noise in AM and FM radio broadcasts, which are among the few century-old information technologies still in use today. The term noise is used to refer to the physical sources or causes of random errors. Most modern information systems use digital technology to reduce random errors caused by noise. Older systems, such as AM and FM radios, use analog technology. An AM radio system uses the amplitude parameter of the radio wave to carry the broadcaster's voice volume information, which is a real number. In an analog system, error-inducing noise is not only accumulated but more problematically amplified. In a digital computer, the smallest information carrier is a pair of transistors, whose voltage serves as the information carrying parameter. 0 volts represents the hardware code 0, and 5 volts represents the binary value 1. The hardware codes are the integers 0 and 1. In a digital system, errors are corrected at each step so that noise is not amplified. Let us see what happens if noise changes the voltage of a pair of transistors from 5 volts to 4.1 volts. In an analog computer, the voltage represents the code of the real number 0.82. A digital computer, however, treats this as an error of code 1 and restores the transistors to 5 volts. The mechanism is similar to the snap objects to grid feature in drawing software, which assigns an object's position to the nearest grid point. The same idea is illustrated by the way a tossed coin settles on a table surface. The original assumption of physicist Richard Feynman was that ideal quantum systems do not suffer from noise. Therefore, a qubit can carry a pair of complex numbers with infinite precision and without error. Of course, the difficulty of building quantum computers lies precisely in achieving such ideal systems. Let us pause here for 2 exercise questions. In the previous lecture, we reviewed the fundamental concepts of information theory and explained that codes and carrier parameters are different forms of information representation. We now turn to the fundamental concepts of quantum physics to understand how quantum waves can be used to carry information. Many of you may already know that the essence of quantum physics is the so-called particle-wave dual nature. The wave nature tells us that the smallest components of the physical world are waves. As engineers, we recognize that a wave, such as the radio waves used in Wi-Fi, has many parameters and is therefore a natural candidate for carrying information. Physicists knew that the electron was one of the smallest building blocks of matter, but its wave nature was not recognized until Bohr proposed it about 100 years ago. The particle nature should really be called the quantum nature. It tells us that the energy of light is discrete, and that the mass and charge of electrons are also discrete. Physicists have known the discrete nature of electrons since their discovery. Light, however, was long assumed to have continuous energy. Its discrete nature, and thus the existence of a smallest unit of energy, was not discovered until Planck proposed it in 1900. Einstein confirmed this idea in 1905, referring to a light wave with 1 unit of energy as a light quantum. Today, we call this a photon. Referring to photons and electrons as particles is a historical mistake and a major source of confusion. It underlies many of the puzzles in teaching quantum physics. This is why Richard Feynman famously said that nobody understands quantum physics. The prominent physics educator Art Hobson has also written critically on this issue, stating, "There are no particles, there are only fields." Experiments, especially double-slit experiments, have consistently shown that photons and electrons can be divided in space and time, and therefore do not behave like classical particles. Only their energy, or in the case of electrons, their mass energy, is not divided in detection. Now let us turn to the question, what exactly is a wave? In everyday life, people often picture waves on the surface of a lake. In practice, the waves we encounter most often are radio waves and light waves, which are used in Wi-Fi, cellular, and fiber optic communications. We define a wave as anything that vibrates in time and can propagate through space. For radio and light waves, the electric and magnetic fields vibrate and propagate, which is why they are called electromagnetic waves. In this course, we may use the term light wave to refer to all types of electromagnetic waves without distinction. For an electron wave, we do not know exactly what is vibrating because the vibration does not correspond to a directly measurable parameter. However, we do know that its vibration can resonate with that of a photon and that it can be described by a wave function. The simplest wave exhibits sinusoidal vibration and propagation and can be described by a sine or cosine function. For physicists, the wave function fully characterizes a wave, and much effort is devoted to solving wave equations. Engineers, on the other hand, need only focus on wave parameters, which are used to carry information. From an engineering perspective, the discrete nature of the energy or mass parameter is an attribute of a digital system, and noise and errors in that parameter are naturally eliminated. This is a major advantage of quantum technology in addition to concurrent computing. A qubit is made from either a light wave with 1 unit of energy or an electron wave with 1 unit of mass. Its wave nature provides many possible information-carrying parameters, while its quantum or discrete nature eliminates errors in its energy or mass, which is the most significant source of noise-induced errors in other information systems. Light waves and electron waves each have 6 independent parameters. The period is the time required for one full vibration. Phase specifies where a new cycle of vibration begins. Wavelength is the spatial extent of one full cycle of propagation, with components in 3 spatial dimensions. Theoretical studies therefore often use a 3-dimensional wave vector instead. Amplitude is the height or strength of the vibration. Polarization describes the direction or angle of the vibration. For a radio or light wave, it is the direction of the electric field. For an electron wave, the equivalent is called spin. In Wi-Fi and cellular communications, pairs of amplitude and phase values of radio waves are used to represent information. In long-distance fiber optic communication, both polarization and phase carry information. The same applies to photonic qubits, where polarization and phase serve as the information-carrying parameters. Let us pause here for 2 exercise questions.